So I want you to think back to the lectures on transmission lines, and what we found in our lectures on transmission lines was that whenever we created what we called an impedance boundary between a T line and some other electrical element, we said that there was a reflection coefficient at that boundary. And so in this case, there's two reflection coefficients, and what we know that there was a V bar plus, which is our magnitude and phase of the incident voltage wave, and then at that boundary, some of the voltage gets reflected, and we call that V bar minus, the magnitude and phase of the reflected voltage wave, and of course there's a transmitted voltage wave. We didn't give that a name in transmission line analysis, but I think it's clear that if some's incident and some's reflected, some also gets transmitted through. And we quantified the percentage that gets reflected as the reflection coefficient, right? We said that the reflection coefficient, in this case at the load, is equal to the ratio of V bar minus to V bar plus. This tells us the reflection coefficient, and in general that's a complex number, therefore it's indicated as a vector, right? And that was a specific example of what happens at an impedance boundary for a voltage and current waveform, which is a specific case of the more general electric and magnetic field traveling from one medium into a second medium. So when an electromagnetic wave changes mediums, as shown here with the two different colored blocks, an impedance boundary is encountered just like it was in the transmission line. At this impedance boundary, just like in the T-line example, some of the wave will be reflected and some of the wave will be transmitted. In this case, we have to consider the transmission of the incident E field, the incident H field, and the incident pointing vector. And we have to consider the reflected E field, the reflected H field, the reflected pointing vector, and then finally we have to consider the transmitted E field, the transmitted H field, and the transmitted pointing vector. So the situation is the same for plane waves traveling in two disparate media as it was for a voltage and current waveform going from a T-line into some sort of ideal load. At this impedance boundary here, we can develop a relationship for the fraction of the wave that is transmitted into the new medium. The fraction of this wave that's transmitted is going to depend on two factors. One, it's going to depend on the intrinsic impedance of the two mediums, so N1 and N2. And that makes sense. That has an analog to what happened in the transmission lines. We had to know, remember, reflection coefficient, its actual calculation was ZL minus Z0 over ZL plus Z0. So we know that the transmission from medium 1 to medium 2 is going to be dependent on intrinsic impedance here, where N1 is the impedance of material or media 1, and N2 or eta 2 is the impedance of media 2. So that's the first thing that the transmission is dependent on. The second thing that the transmission is dependent on is the angle that the EM wave forms with the impedance boundary. So this, we can see that the power vector is perpendicular to the impedance boundary, but you could certainly imagine a case in which the wave came in at some other angle other than perpendicular. So when discussing plane waves, we have to include calculations for eta as well as what we will call the angle of incidence with the impedance boundary. In addition, we have to consider the polarization. So let me write this, the angle of incidence, and then there's a third thing, and that's polarization of the wavefront. So there are actually three factors. So here we just had one factor. Now we have to consider three different factors. And I said two earlier because angle of incidence and polarization are actually, as we'll see, related to one another. So in today's lectures, what we're going to do is we're going to investigate three different situations. Those are called the TEM mode, the TM mode, and the TE mode. And to start with today, what I want to go into is the TEM mode, which stands for transverse electric and magnetic mode, TEM mode. And what do we mean by transverse electric and magnetic, or the TEM mode? By transverse, we simply mean that the E field and the H field are both parallel to the plane of incidence. So this figure that I'm showing right here illustrates the TEM mode. This is the TEM mode. I see that the E field is parallel to the impedance boundary here, and the H field is also parallel to the impedance boundary. It's coming out of the page. So what is perpendicular in the TEM mode? The angle of incidence of the pointing vector here is perpendicular. So we've got the TEM mode, means that E is parallel to that direction, means that H is parallel coming out and into the screen, and that the pointing vector is therefore impinging on the surface of this impedance boundary at a right angle. So that's what we mean by TEM mode. So the general form for the incident electric field is going to be that we've got E bar I of Z comma T. So this is an equation for the incident field that's coming in this direction. It's going to be E0 I, so it's just the magnitude and phase at the origin, or where it started at. It may or may not see some attenuation as it travels. We model that by e to the minus alpha 1 z. And then we've got cosine of omega t minus beta 1 z, and it's got to be traveling in some direction. In this case, this is the z direction. This is just something that's perpendicular to the z direction. I'm just going to call it a hat x. It's just indicating that it's perpendicular to the direction of the pointing vector here, as I've shown in this figure. So again, this is the magnitude and phase of the electric field wave as at the origin. There's some attenuation or not as it travels. The reason I gave it alpha 1 is because that is the attenuation constant of media 1 here. We've got cosine of omega t minus beta 1. Again, I have to be specific with that beta. That's the beta in media 1. Beta will change in media 2 because it has different material properties. And as we know, beta is related to the material properties and the frequency, right? And then, again, beta is related to the distance vector that the wave is traveling in this case, z, right there. So that's the general form of the incident electromagnetic wave. Most often, as you should be used to doing right now, we are going to write that as a phasor. So here I am just putting that into phasor form. And as we usually do in phasor form, we're just suppressing the cosine of omega t term. So that's the general form, and here we have the phasor form. So in problems related to plane wave incidence at a impedance boundary, usually this is what is given to you right here. And I want to point out that this is an I right here. This is the initial value of the electric field of the incident electric field, which is this guy coming in this direction right here. I don't know if you guys can read that in the video, but on your slides it should be clear that that's EI. A lot of times physicists draw this S down here for these electric field vectors, and they'll put an S down here. Sometimes I drop that off. Just know that I mean the same thing there. Anyway, so we've got the incident electric field, and it's got an analog, the incident magnetic field, H bar, S of I. It's got an initial magnitude and phase associated with it. It also gets attenuated in medium 1. It also has a cosine form to it. And if the, oh, I made a mistake here. That should be a hat x. If power propagation's in the z direction and we've defined electric field pointing in the x direction. This guy's got to point in the y direction. So that's the general form of the magnetic field that is incident on the impedance boundary. And a lot of times what we'll do is we'll make a substitution using eta, the impedance of media 1, the intrinsic impedance of media 1, and we'll just write this as E0I over eta of media 1, e to the minus alpha 1 z e to the minus j beta 1 z a hat y. So most of the time you'll see the magnetic field, the incident magnetic field, written in this form right here. So that's the incident electric field and the incident magnetic field. We have two others. We have the reflected and the transmitted. So what are their general forms? I guess maybe write incident here. Start with reflected. The reflected wave is indicated by putting an R in the superscript here, and it's whatever its initial value is, E0 of the reflected, e to the alpha 1, it's still in media 1. That alpha does not have a minus sign on it because it's traveling from left to right. And then we've got e to the plus j beta 1 z, it's still going in the a hat x direction. And then hs, the reflected magnetic field component, is equal to h0r e to the alpha 1 z e to the plus j beta 1 z a hat y, which is often written as minus e0r over eta 1 e to the alpha 1 z e to the j beta 1 z a hat y, where we've just used the fact that eta is equal to negative the reflected magnetic field amplitude and phase to the reflected magnetic field magnitude and phase. So we've just used that right there. So that's the reflected waves. And we can create a relationship for the magnitude and phase of the reflected magnetic field or electric field based on the material properties of the two media, and we call that the reflection coefficient. We give it a special name, the TEM mode reflection coefficient, and that is eta 2, the intrinsic impedance of material 2, minus eta 1, the intrinsic impedance of material 1, over N2 plus N1. So that's the reflection coefficient, and the information that this gives us is it allows us to replace this in the equation. It tells us that the reflected initial magnitude and phase of the electric field component is just equal to the reflection coefficient for the TEM mode times whatever the incident magnetic field component or electric field component was. So that gives us our reflected wave information, and then finally we need to calculate the transmitted wave. And we have E transmitted is equal to whatever the initial value of the wave is in the transmitted medium, e to the minus alpha 2z e to the minus j beta 2z, still moving the a hat x direction. We have a magnetic field hs of t is equal to E0 transmitted over eta 2 e to the alpha 2z e to the j beta 2z, and it's still pointing in the a hat y direction. We can relate the magnitude of the transmitted electric field component to the incident electric field component through what's called the transmission coefficient, tau. And for the TEM mode, tau is equal to 2 times N2 over N2 plus N1. And that is, as you will find, equal to 1 plus the reflection coefficient, the TEM, and the transmitted portion of the electric field is just equal to the transmission coefficient for the TEM mode times the initial amplitude and phase of the incident magnetic field component. Just like for a transmission line, we can have a standing wave ratio, and the SWR for the TEM mode is just equal to 1 plus the magnitude of the reflection coefficient for the TEM mode divided by 1 minus the magnitude of the reflection coefficient for the TEM mode. So a lot of new symbology in this, but the behavior of the TEM polarization mode is almost identical to what we calculated for the T line, and that is because voltage and current in a transmission line propagate in the TEM mode. This is a specific application of TEM propagation.